Well, it's really my very, very great pleasure to introduce our speaker today, who's going to talk about a topic of incredible interest and concern. And I'd also like to welcome everybody to this is, I think, about the fourth or fifth distinguished lecture in our 75th anniversary celebrations of Ames Research Center on the Director's Colloquium Series. So, 75 years, you ain't seen nothing yet. Just wait for the next 150. If we survive asteroids, that's... Now, our speaker doesn't need much introduction, but I'll do that anyhow. Rusty Schweickart received his Bachelor of Science in Aeronautical Engineering in 1956 and his Master of Science in Aeronautics and Astronautics in 1963, both from, there's a small East Coast college, you might have heard of, MIT, I think it was called. I think it's still there, isn't it? Yeah. That's not a bad start. You hear that, you Stanford guys? Rusty served as a fighter pilot in the U.S. Air Force and the Massachusetts Air National Guard from 1956 to 1963. He joined NASA as an astronaut in October 1963. He served as lunar module pilot for Apollo 9 in March 3 to 13th, 1969, logging 241 hours in space. This was the third manned flight of the Apollo series and the first manned flight of the lunar module. In 1977, Rusty worked on the staff of Governor Jerry Brown. You might have heard of that name. He's back again, of California. In 1979, Rusty was appointed Commissioner of Energy for the state of California and responsible for all aspects of energy production. In 1985, he founded the Association of Space Explorers, AS&E, and he particularly founded the AS&E Near Earth Objects Committee, which submitted to the United Nations Committee on the Peaceful Uses of Outer Space, better known as COPUOS, the seminal report, Asteroid Threats, A Call for Global Response. He is co-founder of the nonprofit B612 Foundation with Ed Lieu, who's also here, also an astronaut, and served as its chairman until 2011, is currently chair emeritus on the board of directors. His talk today is entitled Dinosaur Syndrome Avoidance Project. What a cool name. How goes it? Without further ado, Rusty, welcome back to that.
Okay, as Pete said, we're going to do a summary here of what I call the Astronaut Syndrome Avoidance Project, which means don't get killed by asteroids. Or extincted, not just killed, but driven into extinction. This is going to be top level and comprehensive, which means it's impossible to get done in the time, but we're going to try to do it fast and leave time for Q&A. Let me say that it's a special privilege being here today because 45 years ago today, the Apollo 11 crew was on their way to the moon. They launched yesterday, 45 years ago, and on Sunday they will 45 years ago, land on the moon. I flew in March of that year, and it was a tremendous privilege to be part of Apollo and that great time. I'll say something more about it later. So I'm wearing two hats for this talk. The B612 Foundation, which Ed is now leading, deals with the technical issues of planetary defense, whereas the Association of Space Explorers, which is our professional organization of astronauts and cosmonauts, has been dealing for the last 8 years with the geopolitical elements. Again, we're going to get into that, but first, this is a mandatory message from my wife, who unfortunately couldn't be with us today. It says at the bottom, my husband has a morbid fear of asteroids. We'll ignore that. Let's see if the interface works. Okay, so the popular conception of what happened to the asteroids, oh, whoa, dude, check out this awesome asteroid. It's getting bigger by the second. Hurry up before you miss it. But the one I like is Mr. Dinosaur looking at Mrs. Dinosaur and saying, that dress kind of makes you look fat. That'll do it. So this is what we're talking about. This happened, has happened millions of times in the history of the Earth. Not exactly like this. That's a pretty big asteroid, and you'll notice city lights. And so that didn't happen when those were around. But other than that, you get the idea. When I grew up and was the age of most of the people in this, some of the people in this room, the kids anyway, our solar system was 9 planets and the sun. Everything was well behaved, you know, and we had 9 of them. Now we only have 8 planets, thanks to Neil Tyson. But that's not the solar system. The solar system really looks like this, with the main asteroid belt and the inner planets of Mercury, Venus, Earth, and Mars. And the red dots are the ones that concern us, the ones in the inner solar system that are near-Earth asteroids. Those cross the orbit of the Earth, and if they cross the orbit of the Earth, then there is a potential for impact. And those are the ones which we have been recently looking at, and the subject of our whole issue of planetary defense and protecting the Earth from those impacts. Well, the evidence for those red objects that swoop into the inner part of the solar system and come past the Earth and the Moon are all of the craters on the Moon. You don't have to be a rocket scientist to recognize that there have been one heck of a lot of impacts on every body that you see where you can see a surface, where it's a solid surface and not a gaseous surface. This is an interesting shot of the backside of the Moon, and of course you can see that the craters are not only all over it, but they overlap one another. I mean, you got craters on craters on craters. Again, you don't have to be a rocket scientist to realize that that we would look like that if we didn't have an atmosphere and tectonic plates and weather and all of the rest of it that protect the Earth from the smaller asteroids impacting, and that erase the larger ones that did impact and make holes in the surface of the Earth. It didn't erase all of them. We'll see one in a moment. Asteroids come in many different sizes and shapes, all of which are interesting. The biggest ones here are main belt asteroids. They don't come we don't have any that are hundreds of kilometers across that come in across the Earth's orbit. But this one up here is Eros, is the second largest near-Earth asteroid or near-Earth object. I'll use those terms interchangeably. And that's 33 kilometers long. So that's, figure, the biggest one. In fact, the biggest one's about the same dimension. It's just more spherical than that. So it's a little more massive. But I, in particular, want to call your attention to one that's on this chart called Itokawa. And Itokawa, the Japanese have visited. We'll see a picture of it in a moment. It's a dot that you can't even see on this screen. It's about a pixel in size up there. And here it is, close up, picture taken by the Japanese. Like this object here, this is probably what we call a contact binary. That is, in all likelihood, there's a big mass in here with a bunch of rocks and dust and everything, and another big mass here. So these are really two objects kind of that got stuck together. We call it a contact binary, and a lot of the asteroids and apparently even the comets show that characteristic of being contact binaries. So you're dealing with something that's 520 meters or something on the order of 1,700 feet from one end to the other. To give you some relative scale, there's Hangar 1 outside the door here. Okay, so you picture how big Hangar 1 is, and now you got the relative size there with Itokawa. Before we leave this, I want to show you that's about a 20-meter long boulder on the surface, and that's about the size of the object that came in over Chelyabinsk last February. You've all seen the movies of what happened last February, the 13th, February 15th, excuse me, 9 o'clock in the morning. It was a very interesting day because astronomers all over the world were waiting for asteroids to happen that day. But in fact, it was this one, which was DA-14, which was coming sort of by the Earth very, very close south to north. And so everybody had all their telescopes and their this, that, and the other thing ready to capture this asteroid. And then, lo and behold, early in the morning, the Twitterverse came alive, and it turned out that one this size actually came in that same day that this one went by the Earth. One that size hit over Chelyabinsk in Russia. Now, don't ask me why Russia. We're very happy that most asteroids seem to hit in Russia. Particularly appropriate given the geopolitical situation at the moment. In any event, you can see by the shadow, this is about 45 meters or 45 yards in dimension. This one's only about 60 feet or 20 meters in length. And yet, when that came in over Russia, again, unfortunately, the movie isn't here, but all of you know that this thing came streaking through the sky, much, much brighter, an order of magnitude brighter than the sun. Everyone said, what the heck happened? And here's this big streak down through the sky, and everyone ran over to the windows to look out and see what happened. And then the shock wave hit, broke all the windows, and cut everybody's face. So you have a lot of people with superficial cuts and a lot of superficial damage to something like 1,700 buildings. But that was a very, very small asteroid. In fact, we did not expect that an asteroid that size could do the kind of damage that it did. And so the experience last year, in Chelyabinsk told us that, in fact, even the small ones can do a bit more damage than we thought was possible. They also happen to hit a little more frequently than we thought. I'll mention that a little further on. Well, the one that was the size of DA-14, about 45 meters in diameter, is the size of the one that happened in 1908, came down again in Russia, in Siberia, the so-called Tunguska event. And these are sort of, that's an artist's rendition of it, but this is actually a photograph of the forest, which was laid down 360 degrees, about 800 square miles of Siberian forest was blown down and ignited and burned. If that had happened over a city, here that impact zone is superposed on, I think that's London, isn't it? Or is it Washington, D.C.? It looks like London. So you can see that that area of total destruction would be bigger than something like any metropolitan area on the Earth. And if you knock down trees like that with a shock wave, let me tell you, you knock down people and buildings as well. So generally speaking, asteroids of that size, we refer to, I should say, the Congress, thank heaven, referred to them as city killers. So we have happily adopted the term city killer. That is not to imply that these things always hit over cities. They obviously don't. But if they did, it would basically wipe out everything in such a city. Now, some of you have seen Meteor Crater. As I said, there are some impact craters that have happened relatively recently that are still available to see here on Earth. There are probably about between 190 and 200 of them that you can see. This is a pretty dramatic one. It's about a mile across, not quite. And there is a visitor center here. And for those of you who might drive through Arizona anytime, divert and go there if you haven't been there. It is well worth going to see Meteor Crater. This, again, was about the size of the one that came in over Russia, the Tunguska event. This is a city killer, and you can just picture, the shock area that would have killed anything living is way outside just the hole in the ground. And about half of the energy of this asteroid as it came in already dissipated into the atmosphere by the time it hits. So the hole in the ground you're seeing is really only about half of the energy involved. That was probably about, I don't know, what are we saying, 3 or 5 megatons or something like that. Okay, so let me emphasize a couple of things here. This, number one, asteroids aren't something that hit the Earth way back then and no longer happen. This is an ongoing process, and it's an ongoing process at all sizes. It's not just the little ones that hit today. There's still the big ones out there, and the flux, that is the rate at which these things impact historically, is essentially constant. So we are, frankly, at risk with millions of objects out there, everywhere from something as small as, say, 25 meters all the way up to something on the order of 10 kilometers. That's about the size of the one that caused the mass extinction that wiped out the dinosaurs 65 million years ago. Those hit about once every 100 million years, and they have about 100 million tons, megatons of TNT equivalent. I mean, that's unbelievable. That size event wipes out most of life on Earth, and it did it probably several times. Certainly it did it at the KT extinction 65 million years ago. That's a long time between impacts, however, and so life grows back up again and diversifies, and then it gets wiped out again. I mean, this is a process that's happened many times to life as it's emerged here and developed on the Earth. At the smaller end, however, you're talking objects like the one a little bit larger than the one that hit over Chelyabinsk a year ago. That happens about once every 70 years. A city killer, about 50 meters or a little bit smaller, happens about once every 200 to 300 years. Now again, I want to emphasize that these city killer asteroids, while they hit once every 200 years or so, they only hit a city about 0.2% of the time, or maybe once every 50 to 100,000 years, a city would get wiped out. But we have a good idea of this population. We've been looking at these things. We know statistically what's out there, but if we want to protect the Earth from impacts, you can't protect yourself from a statistic. You've got to know specifically what's coming at you, how often, when, how much energy, et cetera. So the whole process of planetary defense and protecting the Earth from asteroid impacts boils down to 3 fundamental challenges that we have to meet. We have to know where they are and what their trajectory is, and project ahead and say, is this one going to hit, and if so, when, et cetera. That is an early warning process. The next thing, of course, if you know something's coming at you, is you got to be able to do something about it, and that's a deflection capability. You got to be able to change the trajectory of that asteroid slightly so that it misses the Earth instead of hitting it, and we call that deflection. Those 2 are basically technical issues. The third one is really a geopolitical issue, and that is you can know something's coming at you, you can have something to do about it, but somebody's got to make the decision. Who pays for it? Who handles the liability if something goes wrong? Who takes the responsibility? There are a million questions, geopolitical questions that come up in it, and we're going to hit that very briefly. So the first 2 of these technical issues are the things that the B612 Foundation has been working for the last 10 years, early warning in particular for the last 2 years under Ed's leadership. The third issue, the standing geopolitical process, the Association of Space Explorers has been dealing with the United Nations, or through the United Nations. And I'll again summarize that work and tell you where we stand. Okay, so early warning, we take those one at a time. Early warning we've been doing through telescopes located here on the ground, usually out in the desert, And there are a number of these around the world, most of them in the US, but some of them in Hawaii. Once in a while, that one is in Hawaii. Come on. Okay, there we go. Once in a while, if they come close enough to the Earth, we can not just look at them with optical telescopes, but we can get radar on them. And this is the big Arecibo radar dish in Puerto Rico. And there are a couple of radar systems around the world. And they tell us, they give us a lot of good information, because radar will give you precise information on the range to one of these things, how far it is, precisely. Whereas optical, you don't get much information on range, but you get where it is, pointing up and down, left and right. So the two of these, optical and radar, are a great combination. But again, you're locked to the Earth, and there are some real problems with that. There's been one telescope called WISE, which was a wide area, let's see, what does it stand for? Wide infrared space something or other. In any case, it's an infrared telescope in space. It was really built to do astronomical work, but in addition, it picked up a number of asteroids. But again, all of these things are very limited, and to date, we have only found about 1% of the asteroids that threaten life here on Earth if they hit. And so a couple of years ago, B612 Foundation, under Ed's leadership, decided to shift from the work that we had been doing on deflection to focus on finding them. Because if you don't find them, there's nothing else that counts. I mean, you got to know what's coming at you. And so we shifted our priorities and decided to come up with and put into space a telescope which would find the bulk of the asteroids that really pose a threat to life on the planet. And this is our Sentinel telescope of B612 Foundation. It's based on a Kepler bus. I'll show you an animation here. Again, this is an infrared telescope in space, communicates with the ground. We put it in an orbit closer to the sun, about the distance from the sun as Venus, and it has its back always facing the sun, looking outward away from the sun. And of course, if you're in around the distance of Venus and looking away from the sun, you're going to have the Earth's orbit out there in front of you all the way around the sun. In infrared, we're not talking about reflected infrared, the sunlight that reflects off asteroids. We're talking about the heat that's emitted by these asteroids as they go around. The sun will take what's about the brightness of a piece of charcoal, and it will make it very hot. Okay, it's about like touching the roof of your car on a summer day or walking on black asphalt. You know, it's pretty hot. And those asteroids will show up as bright spots on a very, very black sky. So infrared, the combination of infrared and being inside the Earth's orbit looking out, is the combination that Sentinel will use in order to detect all of the asteroids of sufficient size that cross the Earth's orbit. Here's the Earth's orbit. This is the orbit of Sentinel, and it's looking away from the sun, as you can see, and it sees the Earth's orbit all the way around. And we basically look at and discover all of the asteroids that cross the Earth's orbit. We then track them, and you can then predict 100 years ahead of time whether or not each of those asteroids poses an impact threat. Okay, if we go on. All right, so this is basically the record of what's been done so far. These are the known Earth asteroids up through December of 2013. Over 10,000 total asteroids have been discovered. The large ones here, the red ones, we've discovered about 95% of all of these large ones over 1 kilometer. But that's a very small percentage of the total asteroid population that can do real damage if it hits. And you can see that over a period of 15 years or so, we've only discovered about 1,000, or 10,000, excuse me. And as I said, there are many, many more of them out there. And here, if we go out to 2025 and assume Sentinel, that line, this point here, comes way down there, and then the total population we're going to discover goes way out the roof of the building here. We will have discovered over 1 million asteroids by 2025, 100 times more than we've discovered in the past 10 years. And of those over 1 million, about 300,000 of them will be the city killer size or larger. So we're talking about a huge population. Of that 300,000, about 4% of them will have some non-zero probability of impacting the Earth. In other words, some probability of impacting the Earth in the next 100 years. That's about the statistics that have been developed so far. So we can expect after 2025, we will have an inventory of somewhere around 12,000 asteroids that have some probability of hitting the Earth in the next 100 years. And we've got to watch those carefully and track them. And if, in fact, that probability increases beyond a certain threshold, we're going to have to take action to deflect them. Okay, so what do we talk about with deflection? Here's where I'm going to get into a little bit of technology, but not much. It's very superficial, but this will help you understand the geometry of the problem that we're dealing with. So if the sun is up there, the Earth orbiting like this along the green line, let's say we have an asteroid that's crossing the Earth's orbit on its own trajectory like this. Of course, there's another set of asteroids that cross the other direction. But we'll take one here, one that's coming outside in toward the Earth. And of course, if the Earth is at that intersection, and let me hesitate for a moment, that intersection is very special because clearly this is a two-dimensional plot, okay? But, so the question is, at that intersection, how far apart are those two lines? How far apart are those orbits where they intersect in 2 dimensions? And about 4% of the time, the distance between those two lines vertically, if you will, is less than 1 Earth radius. In other words, in those 4% of cases that we've seen so far, if the asteroid and the Earth are there at the intersection at the same time, they're going to hit. And that's what an impact is. Let's go back here. Let's say we've got an asteroid and we're able to project ahead 20 years that this asteroid is going to be here at the time that the Earth is here, going along this path 20 years from now. And as we go forward, say a week or 2 at a time, that's the progression. The Earth moves along its orbit, the asteroid along its orbit, and of course, if they both get to the intersection at the same time, you've got an impact. Okay, now let me point out that this is obviously an issue of timing, because if the asteroid were a little bit slower, a little bit behind those points, the Earth would get through the intersection before the asteroid got there. Or if the asteroid were just a little bit ahead of these points, then the asteroid would get through the intersection before the Earth got there. So if we know that there's going to be, if we're projecting ahead and we're going to see that there's going to be a collision, the whole challenge of deflection is to change the orbit, change the speed of that asteroid just a little bit, so that 20 years later, at this time, the asteroid arrives at the intersection before the Earth does and gets through it, before the leading edge of the Earth, or that we cause it to arrive a little bit slower, to be a little behind this point, and therefore it will allow the trailing edge of the Earth to get through the intersection before it arrives. It takes the Earth about 8 minutes from the time the leading edge gets to the intersection till the trailing edge goes through it. So the real question is changing that asteroid's arrival time here 20 years downstream by something like 8 minutes. And that will allow, that's a deflection. We have successfully prevented an impact if we do that. Well, how do we change the speed of an asteroid? Before I leave this diagram, I'm going to ask you in a couple minutes to think of yourself on this asteroid looking at the Earth as you get closer and closer. You're going to be on this asteroid riding toward the Earth in just a moment. But to go back to deflection, okay, how do we change an asteroid's speed? Well, run into it. Kinetic impact, you simply launch a spacecraft, a bunch of water, sand, electronics, whatever you got, doesn't matter. Just launch something and run into the sucker. Rear end it, okay? Rear end it if you want to make it go faster, or front end it if you want to make it go slower. Pretty simple. Not exactly, it is rocket science, but it's sort of rocket non-science, I guess. Okay, well that's pretty robust. You can launch a big mass and you can run into it pretty fast, and you can probably change its speed by, a fraction of a mile an hour, and that's enough. It doesn't take much of a change of speed, but those suckers are pretty big. So, okay, on the other, oops, let me go back one here. Went the wrong way. Okay, pardon me for stepping through this again. Okay, so the problem with the kinetic impact, I'm going to catch up with you here for a moment. The problem with the kinetic impact is that while it's pretty robust, you can get a pretty good impact and change of velocity, it's imprecise. You don't know exactly what's going to happen. And what you don't want to do is just leave this thing in some random orbit. You want to know ahead of time what the orbit change is precisely that you give it. So the way you use these two things in conjunction, we get a brute force change in velocity here, and then we use a gravity tractor where we have a little spacecraft. Let's say we got an asteroid here, and we got a little bitty spacecraft. We go up there and we hover in front. Let's say this asteroid's moving this way. We hover in front of it, and if we stay there, we have little thrusters, and we stay in front of it at a fixed position. The mutual gravity between this object, this spacecraft, and our asteroid is just enough that that gravity is now pulling the asteroid with us, behind us. So we're using gravity, very weak gravity force, as a tow rope without ever touching the asteroid. We don't land on it. We don't care if it's tumbling. We don't care what it's made of. It can be dust. It can be big rocks. We don't give a damn. As long as it's got mass, we're going to have a gravity effect, which is going to tow it, and make a very small but precise change in the orbit. That's what deflection is about, changing the speed a precise amount in order to miss the Earth. Of course, if it's too big, we use the big dog. We won't talk about that one. We don't like it. Nobody likes it. But, it's always there in case the asteroid is too big. All right, now we're going to go to the third element. We can know something's coming at us. We have something we can do about it. Who does it? Who decides who does it? Who pays for it? All that, okay? Now I'm taking you, you're riding on the asteroid, remember, and you're coming toward the Earth. You're looking at the Earth as you get closer and closer. Here's your view of the Earth. This is just an example. The Earth could be any orientation here, but let's just take this as an example. And let's just say that is the plane of the asteroid's orbit. You are approaching the Earth in this plane that cuts through the Earth at that point, along that line, okay? So now, if you hit the Earth, you're going to hit somewhere between the trailing edge here, the Earth is moving to the right, and the leading edge. You're going to hit along that line, okay? That red line we call the risk corridor. And in fact, we don't know precisely what the timing is. So in fact, you may be on a trajectory that takes you out and you pass in front of the Earth and go through the intersection first. Or you may actually arrive at the intersection after the Earth, in which case you're going to actually be out here. So you're going to be somewhere along this line, but we don't know exactly where until we get up there and measure precisely what your trajectory is. Let's just say, for example, we're going to have an impact, and let's just say it's right in the middle of the North Atlantic here. All right? Now, if you make if we go up and deflect it and we make it arrive a little bit early, hello, there we go. Let's say we made it arrive 2 minutes earlier. Okay, then it would hit here. Or if we make it arrive 4 minutes early, it's going to be there. Of course, if we make it 8 minutes early, it's over there. That's what we want, okay? But if something goes wrong, of course, it's going to hit in those places. Or we could make it arrive 2 minutes late, or maybe 4 minutes late, or if we want it to miss the Earth, 8 minutes late, and it would go behind the Earth. All right. If you're a Frenchman, what do you say? Okay? Oh, well, let's make it go to the left, right? And if you're an American, you say, well, no, let's take it over, let's take it over to the right. In other words, in order to successfully accomplish a deflection, we're going to be effectively dragging the impact point along the surface of the Earth, along that line, until we get it out here, so that it's no longer going to hit the Earth. But of course, if something goes wrong, these people could be in real danger. So there is risk. Anytime you're talking about a deflection, you're talking about shifting risk and putting people at risk who were not initially, in order to eliminate the risk for everybody. And you, as the president of France, and coming up for an election, are going to have to say, well, do I accept that? You know, do we have a referendum? Well, we got to decide by next week. What do we do? Okay, and so this is the geopolitical challenge of deflection. How do you make a decision? And for that matter, suppose we decide to drag it this way. Do we let Russia do that? Or does the United States do that? Or maybe India? Or maybe if it's 100 years from now, Zambia with their space program? Who knows? Okay? No matter what you do, in order to have a deflection, you have to drag an impact point wherever it is on Earth across parts of the Earth that weren't at risk in order to get it off the Earth and everybody safe. That is a huge geopolitical challenge. Obviously, those are bad. That's good. Those are the ones we want. Okay, there is the back of my head before I had a bald spot. Speaking at the United Nations in Vienna at the Committee on the Peaceful Uses of Outer Space, or as Pete said, COPUOS, and we took this issue to the United Nations and basically said, look, guys, this is a collective decision. The planet is at risk here. Even though there is one impact point, everybody on the planet, that line could be across any country, and typically there are going to be 10 or 20 countries along that line. This has got to be a cooperative planetary effort. And you've got to get together. So United Nations, get organized. Okay, so I'm going to come to the end here. I'm going to give a scorecard of where we stand on these three things. Early warning, okay? Early warning, I'm going to give a B-. NASA has done a pretty good job up until a couple of years ago, when the limit on their telescopes was essentially reached and the curve dropped off very dramatically. The discovery rate is almost, not quite, but almost down to zero. And of course, we're nowhere near finding, the million objects we got to find. But we know how to do it. We've been doing it. It's just that NASA isn't getting the money that's needed in order to get this done. And so B612 Foundation has said, okay, just do it. We'll do it. Fine. So we're doing it privately. And again, it's a B-. We got a lot of work to do, but we know what we're doing. Deflection, we know how to do a deflection. We know it can be done. The technology is not the issue, but it's got to be demonstrated. And we've never been able to get NASA off the dime to actually organize and set up a demonstration of a deflection. Actually change the orbit of a random asteroid that's going by, but it hasn't been done. But on the other hand, it's still pretty early, so let's just say D-, but we're not going to worry about it too much. Okay, the geopolitical, that's the toughest one. I'm going to give an incomplete. This is really the most important issue of the three. Early warning. You can't do anything unless you know what's out there and coming at you. Deflection you don't really need until you have something that's coming at you, but you better be ready. But on the other hand, this one, that's the hardest one. You can imagine trying to get the nations of the world to agree where different nations are going to be accepting risk and somebody else is going to have it eliminated, and whose taxpayers are going to pay, et cetera, et cetera. That's a really, really tough challenge. Now, so that's my scorecard. Let me say, in response to people who say, why the United Nations? Well, the United Nations is the only organization that really represents everybody on the planet, or just about everybody. So, you know, they got a big hat, you know, no cattle, but a big hat. But my God, what a hat, you know. Okay, so coming to the end of the talk here, let me just stand back from all of this and be a bit philosophical. Everybody in this audience and most people in the world who think about these things have thought about, is there life out there in the universe? There must be. In all of the billions of galaxies, and these are all galaxies, there are no individual stars in that image. They're all galaxies, and each of them has hundreds of billions of stars in each of those galaxies. And of course, we know there are planets around, apparently, most stars now that we've seemed to have discovered. So there is lots and lots of planets out there. Is it imaginable that there's not life? I don't think so. We don't have any proof of it, but it certainly is, to me, it's not even a stretch to imagine you know, that there is intelligent life out there. And in all likelihood, in my view, personally, there probably are people who have formed a community from different planets. Who knows? But all of them, keep hitting that, pardon me, all of them live in a solar system, came from a solar system like ours. And we know that different stellar systems have asteroids and comets. You know, we're not unique. So everyone has faced this. And my thought here is that this is, you know, I look at myself. 45 years ago, I flew on Apollo. I had the great privilege of dealing with that challenge of human beings first leaving the Earth and landing on another body in the cosmos. And today, I say that you have this generation, the kids out here in the audience in particular, the students, the interns, it's your generation that has this incredible privilege to deal with the challenge of preventing extinction, preventing these asteroid impacts, which ultimately can lead to extinction, and preventing us from moving out into the universe. So I always like to show this statement at the end, okay? It's likely that if, and I underline if, there's a community of sentient life out there in the universe, that its members have each faced this challenge. That is the challenge of preventing asteroid impacts on their home planet. Otherwise, they wouldn't have made it, okay? They passed that challenge. We humans now face this great test of admission into the life of the cosmos. This is your challenge. We did Apollo. You do this, please. Thanks.
So we have time for a few questions. If you have a question, please raise your hand, wait for the microphone, and stand up and ask your question.
So today's July 17th, 2014. We look up at our telescope and we see something coming at us. How much time do we have to react to actually go through steps 2 and 3 on your list?
If you look up, number one, you're not going to look up and know right away whether something is, quote, coming at us. There is a very slight possibility, very low probability that you can look and see one that's just about to hit, but that would be a total miracle to do that. You look up and you find things moving in the sky, asteroids moving against the star background. You track them, you plot their orbit, and you project 100 years ahead of time, and you say, in that 100 years, is there going to be an intersection? You don't there's no sense that it's coming duck. I mean, that's not the deal. We're talking about being able, the nice thing about asteroids or anything in space, as all of you know here, is that they're predictable. They behave in orderly ways, Newton's laws and all of that. A few other things like relativity, but you know, we can predict where something is going to be in space many, many years ahead of time. And to do our deflection, we need something like 15 or 20 years. So generally speaking, you're not talking about finding something at the last minute, although that is a very, there is a possibility of doing that at fairly low cost, but you're not going to be doing anything there other than, in fact, saying duck. If you see something literally coming at you on final approach, what I call final approach, or what other non-friends call the death plunge, generally speaking, you have somewhere between 2 days and maybe a month to evacuate, the same way you would with a hurricane. But what we want to do is to be able to deflect and prevent impacts, and to do that, we find these things, understand where we inventory this whole array of things, know their orbits, and we know 20 years ahead of time whether something is going to hit. But we have to find it first. That's why the early warning is so important. I can see hands going up, but I don't know who. Oh, there's the mic. Okay.
Hello. You showed us that if we were able to deflect an asteroid, it would come either before or after Earth, but pretty close. Is there a concern of it coming back around again as it makes another orbit around the moon in the future? And would you have to deflect it every single time again?
Yes. I don't know. Are we got the lapel mic going? Okay, there we go. The answer is yes. We make a very, very small change in the speed and the orbit of these asteroids in order to make them miss the Earth. So that asteroid will still be in approximately the same orbit, and it may 20, 50 years, 100 years come back. That's the reason we want to have a precise end deflection capability. Not just hit it and make it miss the Earth, but not know where it's going to go. We want to try to put it in an orbit, a precise orbit, that will say it's not going to be a problem for another 100 years or something. And there'll be different technology, better technology. In the end, we would be able to, in my view, we will be able to, in fact, set up a deflection in such a way that, in fact, it will go somewhere near Venus, close enough to, say, Venus or Mars, on its trajectory, that planet will affect it gravitationally, and it will no longer be a problem. In other words, there is a possibility over a long period of time of getting rid of asteroids. And in fact, I would suggest that one way we're going to be able to tell, ultimately, if we get the right kind of telescopes and things, whether a planet might be inhabited is to say, are all the asteroids in that solar system cleared out of that planet's path? You know, that doesn't happen by accident. You know, that may be a good indicator of life, intelligent life, responsible life.
So when you talked about deflection, you only mentioned deflection making it faster or making it slower. Could you possibly deflect it in other ways, like, I don't know, any of the spatial directions, really?
The answer to that is yes, you can do that, but it's incredibly ineffective. If we can talk about that later, but if you draw the vector, I'm sure you're a vector person, so if you draw the velocity vector of one of these things, and you change its length, in other words, change the velocity, the magnitude of the velocity, you're going to have a cumulative effect. It's going to make the orbit a little bit larger, and it takes or smaller, and it takes the asteroid longer to get around, or a little bit less time to get around. It may change the orbital period by only a matter of a couple of minutes. Okay, but each time it goes around, that adds up. 2 minutes, 4 minutes, 6, 8, 10, etc. So you make a big change in the arrival time. If you change the direction of the velocity of the vector, you do nothing to the arrival time. It's going to hit 5 miles from where it would have hit before you did that. So changing the direction of the vector, the velocity vector, is not useful. You can only affect a deflection by changing the length of the vector. Okay, yes.
Hello.
There we go.
Maybe just for a touch. Anyway, there we go. My name is Gray Marcy, and I just transitioned from Marshall Space Flight Center here to Ames, and had a chance to hear you testify 2 or 3 years ago before Congress on support of the President's plan for commercial space, as Neil Armstrong opposed that plan, and I was honored to be in that hearing room at that time, and that to say, as you've observed NASA funding over the years, and as you've had a chance to speak to our legislators and leaders, how do you see NASA's budget now and going forward to fund the things that you see and you've convincingly portrayed as very important to us as a nation and as a worldwide concern?
All right, well, I'm going to extrapolate a little bit on your question. I'm going to assume that what you're really asking is, how do I see funding for something for planetary defense in comparison with other things in the future? You know, we have, Ed and I and Pete and others have worked on this issue on NASA and on the Congress for a decade and a half, 2 decades. And while people always, once they understand it, understand there's a reality to it and they're concerned about it, most of the Congress has no clue of what an asteroid is or that they impact. They got excited about the one that hit in Russia. And it lasted for about a week or something, 2 weeks. Compared with the potholes in the road, asteroids impacting 20 or 30 or 40 years from now don't amount to a hill of beans as far as most people are concerned. And so while everybody who really understands this issue understands it is, number one, a huge issue, because ultimately, very seldom, but at the largest end, you're talking about extinction, the end of the whole evolutionary process here on this planet. And it doesn't cost much to do it. Nevertheless, the potholes in the road, I'm going to get letters from my constituents next week about this, that, and the other thing, immigration, you name it. So this has never been a high priority for the Congress, and frankly, it has not been a high priority for NASA either, partly because NASA does not and has never gotten clear responsibility from the Congress or the President for this issue, for protecting the Earth from asteroid impacts. And because that authority, that responsibility has never been NASA's, they don't have the authority to ask for the money to do it. So NASA is responsible for space science and for exploration. And any money that goes out of NASA's budget for this comes out of the pocket of graduate students who are doing research on space science or whatever. So the irony is that this is only survival. Who cares, right? Well, we care. We feel that you care because the time horizon on your concerns is perhaps your children or your grandchildren's lives. The time horizon for corporate world is maybe the next quarter. For the government world, it may be the next election. You know, we're talking 2, 4, 6, 12 years. This is a long time. This is survival. So we have gone to the public with B612 and saying, okay, this meets your time horizon for values. This is what you care about, survival, the continuation of evolution, and your own families, for that matter. Okay, last one, yeah.
It's been 45 years since you flew in space. Looking to the future of human space travel, in those 45 years, have you noticed any physiological effects on yourself as a result of that?
Oh yeah, I've gotten a lot wiser.
Space?
No. No, but you know, at some level of detail, I'm sure that there are some effects, and the effect on vision appears to be something real and systemic in spaceflight. You know, you have bone loss, calcium loss, and reduces the density of your bone, but it comes back. You know, there are some long-term effects, but none of them that really are significant compared with the drink you'll have this afternoon, I think. Okay, thank you very much.
Thank you very much.